Hey kids, Smath here. Got another one of these solids videos coming up for you. This one's going to discuss simple cubic or all cubic unit cells. And so let me share a screen with you and try to explain. I think this diagram will show you a fair amount of what I'm looking for here. Just a minute, bear with me while I get connected. There we go. Okay, so we are only dealing with cubic unit cells. That cubic's going to make things real simple because now we know if we know the edge, we can figure out the volume. What we need to look at is the relationship between spherical atoms being placed into a cubical shape, that they don't fit very well. And so here's what I mean by that. If you check out the diagram, I have the three different types of cubic unit cells. We have a simple cubic unit cell, and that simple cubic means simply that the atoms are going to rest on the corners of the unit cell, and that the atoms are going to touch along each edge. What that means is there are 8 sides to this cube. Each corner, there aren't 8 sides. There are 6 sides to the cube. There are 8 corners to this cube, and each corner has 1/8 of an atom sitting on it. See, think about that. If you take a grape or an orange or an apple, cut it in half. Now cut it in half again. Now cut it in half again. Keep cutting. You're going to get down to this 1/8 of a corner. If I have 8 corners, 1/8 of a corner, there is one total atom in a simple cubic unit cell. Now, if those atoms are touching along that edge, then the relationship is quite simple between L and R, that L is going to be 2R. Now we automatically can take the relationship of measuring the radius of an atom and going from the radius to that length of a unit cell. Now that works real easily for a simple cubic because, well, the edges are touching. That's not going to hold true necessarily in the other ones that we're looking at. The other thing to make note of is simple cubics are relatively unusual. They're not very tightly packed. They're only 52% full of atoms, which means they're 48% of empty space. And the coordination number is a fancy way of saying how many of them are nearest neighbors. And if you can look, as the coordination number increases, 6 to 8 to 12, the packing efficiency, things get denser. And that's going to be very common in these unit cells. These are used commonly for metals, a lot of the calculations. So let's look at our second unit cell. Our second unit cell that we're dealing with is body-centered cubic, BCC. Simple cubic is SC. Body-centered cubic, BCC. Now this one has, as the name implies, in the middle of the body centered, has an atom in the middle, as well as all the atoms that are on the corners. So it's like a simple cubic that's had an atom pushed into the middle of the inside of it, which isn't going to work terribly well because, well, now the atoms on the edge aren't touching. We can't just use L equals 2R. Now we're going to have to use a little bit of geometry, a little bit of hypotenuse here. And what we find out is the diagonal of 4R, you guys should be familiar with this, 4R, L, and L radical 2 is the relationship. And so if we simplify that down, the unit cell edge L is going to be equal to 4R radical 3, or 2.309. Okay, and if we look at how many total atoms there are, well, there's one atom on the corners, And then there's one atom in the middle. So there's a central atom, and then there's the atoms on the corners. That would make 2 total atoms. That's body-centered cubic. And if you notice, the nearest neighbors went up to 8, and the packing efficiency increased to 68%. Lastly is called the hexagonal closest packed. This is going to be very similar, for our cases, identical to what's called a face-centered or cubic closest packing. Okay, CCP, cubic closest packing, or face-centered cubic is going to have the same thing. Now, in this case, instead of having one atom that's pushed into the center of the unit cell, now what we have is 1/2 of an atom in the middle of each face. So there is a 1/2 an atom facing in, 1/2 an atom right here, 1/2 an atom right there. Well, it doesn't take long to figure out there are 6 sides to a cube and each side has 1/2 an atom. That's going to be 3, plus we still have all of our atoms on the corners. So 3 from the faces and 1 from the corners. Face-centered cubics have a total of 4 atoms. And their relationship, because we have this diagonal, there's the triangle we can use, and we know that it's R plus 2R plus R again. If we simplify this down using Pythagorean theorem, we're going to get L equals R radical 8. You don't need to understand the derivation. Just understand that for face-centered cubic, L is R radical 8. For body-centered cubic, L is 4R over radical 3. And for simple cubic, L equals 2R. All right, that's unit cell basics. Now, let's take that, let's do a sample problem, use it for a calculation, okay? We have nickel metal, and we're told that nickel crystallizes in an FCC arrangement. So it's face-centered cubic. And they told us with each nickel has a radius of 1.24, and this is old school. They gave us angstroms. No problem. We can convert those. Okay. And what they're asking us to do is calculate the density of atomic nickel. Okay. Should be pretty easy to do. So the first thing we should do is find our radius in a useful term, which in our case is going to be meters and centimeters. So let's take that 1.24 angstroms. And now you can see why they use angstroms. They like that because it's a nice, simple, clean unit. And we told you in the Bragg equation video, 1 times 10 to the negative 10th angstroms equals 1 meter. Well, I'd rather have things in centimeters because we're going to calculate density. Density is probably going to be in the units of grams per centimeter cubed. So let's get things to centimeters. 1 meter, 100 centimeters. We've got a radius now of 1.24 times 10 to the negative 8th centimeters. That's our R. That's our radius. And they've told us now that this is FCC. FCC tells us 2 things. FCC tells us that L equals R radical 8 and that I've got 4 atoms going on here. So if that's the case, L equals R radical 8. And R we just calculated 124, 10 to the negative 8th centimeters, radical 8. The length of this unit cell is going to be 3.51 times 10 to the negative 8th centimeters. That's L. We want density. By calculating density, we need to have mass and volume. Well, this isn't volume. This is length. You guys are already way ahead of me, I'm sure. V equals L cubed, 351, 10 to the negative 8th centimeters, cube it. We're going to get a tiny number, 4.31. 10 to the negative 23 centimeters cubed. That's my volume. That's a nice one. Let's hang on to that one till the very end when we go to calculate the density. Now, to calculate density, we have to have volume and we need to have mass on top. So how can we get the mass? Well, we know that we have 4 atoms of nickel. No problem. We can calculate that from this, 6.02, 10 to the 23rd atoms. 1 mole of nickel and 1 mole of nickel has a molar mass of 58.7 grams. Okay, punch that in. Texas Instruments says this is going to be 3.9 times 10 to the negative 22 grams. So what's my density? That's, clean it up. Sorry. So my density, D equals M over V, 3.9 times 10 to the negative 22nd over 4.31 times 10 to the negative 23rd. This is in grams. This is in centimeters cubed. We're going to get a great number now. The density of nickel, 9.04 grams per centimeters cubed. And that's a very real number. That's something that's very close experimentally to what our known value is going to be. So you can see that by looking at the unit cell, being told how it's bonded, FCC, we know L equals R radical 8. And we know it's nickel, so we know its molar mass. And by knowing the radius of 124, we can get from radius to length, length to volume, and we can go from 4 atoms, because it's FCC, atoms to moles, moles to grams, put grams over volume, we've got density. It's a little bit of calculation, nothing too hard, just a little convoluted with a few calculations and conversion factors that we have in there as well. But that's a basic unit cell density calc. I'm Smath, and I hope this video helped you.